Hello, Chem 1B. This is Chapter 14, Lecture Video 5. And so, last lecture video we talked about how to determine a rate law and how to do some rate law problems. And rate laws are very, very useful. They allow us to calculate the rate at any given set of initial concentrations, or the initial rate specifically. And that's great, but what might be better? And what might be better in this case is we'd like to know what the concentration is after in a given elapsed time, right? Think about like a processing plant that's making chemical and they want to sell this chemical to companies, what have you, right? Well, they want to be making chemical at all times so that they never run out of product, right? Well, after a certain point, the reaction slows down so much that, it's not producing as much compound that they want to sell. So what they might want to know is, hey, after how much time do I need to go in and add more reactants to my reaction mixture so that I keep producing product in a fast rate to keep producing what I need to produce to sell? So knowing how much the concentration is after a given certain time is very, very useful. And this gets us to converting the rate law itself, because it does not have a time variable in it, to have a time variable. Change it so that it has a function of time involved. Now, how do we do that? Now, the short answer is we use calculus. So if we look at the overall first order, we're going to look at a first order reaction because the way this works is different based on the overall order of the reaction. So we have this reaction, A goes to B. One reactant, the rate law for A would simply be this, right? As we hopefully know. Rate is equal to K, some rate constant, times A. This is our rate law. Now, we also know that the rate of this reaction in terms of the reactant A is going to be delta concentration of A over delta T times -1 because we want it to be the rate of the reaction. And we can do that. Now, both of these equal rate of our reaction at this point in time. Now, we can integrate this and get what we call the integrated first order rate law. Now, integrals are not something that's going to be part of this course because calculus is not a prereq for this course. I just want you to know that if you've ever heard of integration or you've done integrals yet, then that's basically what we're doing. Now, I'm just going to give you what the equation actually is. So what is A at some time later, right? We can predict this. We use calculus to rearrange. Now, if you do know your calculus, we're going from concentration of A initial to concentration of A at time t here. And the integration here is t equals 0 to t. That whole setup, you don't need to know how to do the rearrangement, the calculus part. I'll give it to you. It's going to be equal to this. Another version of this equation is not with natural logs, but instead just, hey, the concentration of AT here is equal to e to the negative KT plus A naught. And A naught's just the concentration at time 0. This equation is, you can use either one. I like the one with natural logs because it's a linear equation and it's just somewhat easier in my opinion, but you can do, oh, sorry, not plus, what am I doing? This should be just times A naught. So this one you can use if you want, but I'm not going to give you this one. I'm going to be giving you this equation on the test. Now, if we look at some of the components, this is your concentration of your reactant after however much time has elapsed, right? This is your rate constant. This is the time that has passed for the reaction. And this was your initial concentration. And this whole equation is known as the integrated first order rate law. There is an integrated zero order rate law, there's an integrated second order rate law, and you need to be able to kind of pick them out of a lineup on the equation bank for our test, but I'll be providing the equations for you. You don't need to memorize them. So let's talk about a first order reaction. Let's do a problem, right? A goes to B, C, whatever. We're told, hey, our initial concentration of A is this, and our rate constant is this. What is the concentration of A after 10 minutes have passed? So we can use our integrated rate law, ln of AT, which is what we're trying to solve for, is equal to K times T plus the natural log of A naught. Now, there's a small discrepancy here. If you look, K's units are in inverse seconds, and the time we're given is in minutes. Now, before we can do anything, we need to make sure these units agree with each other. So I think I'm just going to change minutes to seconds, right? Which hopefully everybody knows that conversion. I'm going to do it all at once in this slide. So we have K, it's times -1 because that's part of the equation. And we have 10 minutes. I'm multiplying by 60 seconds per minute here to change it from minutes really to seconds. So the seconds here, you can kind of see they cancel. And then we're taking the natural log of this guy. All of this gives me this, which gives me this. Now, some students stop here, which is really bad. For one thing, you can't have a negative concentration. Concentrations are kind of like an amount of stuff, and you can't have less than nothing. So the negative sign is the clear giveaway that we're not done. And the other bit is we weren't asked for the natural log of A, T. We were asked for just AT, what the concentration is. So we need to know how to get rid of natural logs, and that's by taking E of both sides. So if I do that, these two will cancel each other out. We'll just get AT here, and we'll get E to the negative 3.775, which gives us our final concentration. One thing to always just double check is that this value is in fact less than your initial. As reactions go, concentration decreases. This is the amount of reactant still remaining after 10 minutes. So this is your concentration that's present after 10 minutes, not how much was lost, which is an important distinguisher. So let's do one more. How long does it take for 73% of A to decay? All right. Now, this is a little bit of a trickier problem. We do not know AT or A naught in this case, but we know the ratio of them to each other, right? We want to know, hey, what's AT when we know that AT is equal to A naught times some decimal based on this percentage. Now, here's where things can get a bit tricky. AT is how much is remaining, and 73% in this problem decayed. So that's not how much is remaining. 73% is not what's remaining. It's 27% that's remaining. So I'm going to multiply by 0.27 because 27% is 0.27. Now, with this relationship here, I can kind of plug in, right, to my equation and solve. Now, it's important to note that just by changing literally like one word in this sentence, it changes the problem dramatically, right? So in the problem we're actually doing, I'm asking for how long does it take for 73% of A to decay. If instead I asked how long it takes for A to decay to 73%, this isn't a 27 then, that's a 73, and this would be 0.73 A naught. So you really have to read your questions carefully. But let's continue on. So I've rearranged my equation, right? One of the things that you should know natural log rule-wise is that ln of AT, right, if I subtract ln of A naught from that, which is what I did in the equation, right? If you think about ln AT is equal to negative KT plus ln of A naught. If I subtract this over to that side, then I get this situation on that side of the equation. This is the same thing as the natural log of AT over A naught. Like so. So this converts into that, which you should know about natural logs. So at this point, we can kind of plug in for AT. We know AT is equal to 0.27 A naught. So if I plug that in there, I get this. And I know K. And now I can solve for T because these two cancel. All right? And so what I get is natural log of 0.27 is equal to negative 8.2 times 10 to the negative 4 times T. And I can solve for T just by dividing over and plugging into my calculator, which gives me this. Now, because my K value is in seconds, I'm going to get this number initially. Now, I don't know about you, but 1,597 seconds, that means less than nothing to me. So I'd probably convert this back to minutes. Now, we don't actually have iClickers anymore because we're online, so we're just going to call this a regular problem. The first order conversion of cyclobutane to ethylene, this guy, has a rate constant of this. How many seconds are needed for the concentration of cyclobutane to decrease from there to there, right? So here's my first order integrated rate law, AT is equal to negative KT plus the natural log of A naught. Now, we can just really plug in everything and solve for time, right? So I know that AT is 3.28 molar. And I know that K is 1.12 times 10 to the negative 2 inverse seconds times T, which is what I'm being asked to solve for, plus the natural log of 5.64. I'm running out of room there. And I can solve. Really, the only unknown is the T here, right? So if we just do some calculations, we can get this to simplify to this, right? So we get 1.187-ish, 88 really, is equal to negative 1.12 times 10 to the negative 2 inverse seconds times my T variable plus, 1.73-ish. And now it's just a matter of rearranging and solving, right? So I can subtract over this 1.73 from both sides and get the next part. Negative 0.54 2-ish is equal to negative 1.12 times 10 to the negative 2 inverse seconds times T, and we can just divide over and solve for T. And so this is my answer of how long this would take. All right. Okay, so let's talk a little bit more about the first order integrated rate law. Let's look at this equation, right? This actually is very reminiscent of another equation that you've probably learned about at some point in, I assume, high school math or even before that. And that's this equation. Y is equal to mx plus b, which we hopefully all can recognize as the equation for a straight line. Now, if we look at this whole setup here, we can kind of say, hey, these guys are the same as each other. These two things are the same. I've color-coded it, right? So hopefully that helps. These two things are going to be related. And then finally, you know, these two things, which basically breaks down into y would be equal to our natural log of our concentration at time t. That's our dependent variable. x would be equal to the time, which is our independent variable. The slope of the straight line we're going to get is negative k, the rate constant times -1. And the intercept, the y-intercept, will be equal to the natural log of our initial concentration. So if we graph this, we can get some information out of it, right? So how would we graph it? Well, we'd put time on the x-axis, the natural log of your initial of your concentration at time t on the y-axis. And when you do this, if it's a first order rate law or first order reaction, we're going to get a straight line with a negative slope. The y-intercept will be equal to the natural log of our initial concentration, and the slope of this straight line is going to be equal to negative k. So this provides us a lot of useful information. It allows us to determine k from just graphing some data. It would allow us to determine the initial concentration as well. And finally, if we didn't know whether the reaction was first order or not, if we graphed it in this way with ln of AT on our y-axis and t on our x-axis, and it didn't give us a straight line, that would tell us that it wasn't a first order reaction. So we can also, in some sense, eliminate it as a possibility for the order of the reaction if we wanted to, just by graphing the data, right? If I measured the reactant concentration over time and graphed it in this way and I didn't get a straight line with a negative slope, then I know, hey, it's not a first order reaction. All right, so that's the end of this lecture video. If you have any questions, please let me know.